Good morning, all of you. Shubham Jane. Today's topic would be transformers and also the examples with respect to AC circuits. Now, transformer is a device which works on the principle of mutual induction. Whenever it is the case of mutual induction, we know there are two coils. The one which is called primary coil, the coil which induces EMF, and the other one is secondary coil, that is the coil in which EMF is induced. So with such details, now this is what is two coils. We are showing it as a model, we are showing it as a block diagram. In fact, do remember, when it is the case of mutual induction, the primary coil and secondary coil, mutual induction, to be the most effective thing, it is always the case that the secondary coil is placed inside the primary coil so that the flux linkage with secondary is maximum due to primary. So that is what is the case. So it is secondary placed inside the primary, that will be the case for the maximum or effective flux linkage. But here we are showing a model where it's a laminated plates of iron made it, and this is primary coil. This is a primary coil, and here I show the number of turns are NP. P for primary, N the number of turns, NP. Now this is the other side, the secondary coil with the number of turns, NS. And this is what is the most important element when it comes to the functioning of transformer. Now circuit diagram. This is how we show the primary coil and secondary coil placed very close to each other. So two inductors we show placed close to each other parallelly. And sometimes we will also find that two lines drawn like this between primary and secondary, which means that it is an iron core transformer. Remember, in the discussion of mutual induction and also in the case of self-induction, we have mentioned that when it is the case of capital M. You remember we have given an expression where there is mu naught times mu r in the denominator. I am not giving that complete expression one more time, we just go through that so that you can revise that. So because of that, what happens? Capital M value increases. So capital M value increasing means, yes, the efficiency of the transformer is getting more and more. So this is what is the symbol that can also be used for iron core transformer. Now, based on the mutual induction, the big expression that is the principle used for the transformer is, you see, Vs by Vp, the voltage in the secondary to the voltage in the primary, as the ratio Ns upon Np, number of turns. It is not number of turns per unit length, remember the total number of turns, such that now this factor Ns by Np, this Ns by Np is what is called as transformer constant or transformer ratio. Ns by Np, that is very important. Sometimes whenever it is given transformer ratio, this order is important. It is Ns by Np, not Np by Ns. Now, when we say transformer, which is a device used to change AC voltages, the biggest, really one should say that mutual induction is such a great gift by the nature, using which now, why transformer? In the beginning I should have told you, this transformer is a device which is used to change the AC voltages to the required values. Changing means both ways. Suppose very high voltage is there, those higher voltages converted into low voltage signals or lower voltage signals converted into higher voltage signals. So that is what is the greatest advantage of this transformer. Now, when we say transformer is changing the voltages, but it is not violating the nature or the law of the nature, which is that conservation of energy. Though voltages we are lowering or increasing, no question of any violation of conservation of energy. Therefore, if I use conservation of energy, then the power in the primary should be equal to power in the secondary or vice versa. So conservation of energy relation we are now writing, which gives one more important result, right? So no violation of conservation of energy. So power, definition of power. So this is Vs times Is is Vp times Is. This is how we have defined power, right? Therefore now this Is by Ip we are getting as Vp by Vs. See here, earlier we said Vs by Vp equal to Ns by Np. Therefore Vp by Vs will be Np by Ns. What did we observe? Exactly look at these two expressions, we will find the reciprocal results, right? Therefore Is is equal to Ip by K we can write, right? Is is equal because this Ns by Np becomes K, right? Therefore Is is equal to Ip by K. Now when we have these two equations, now we are introducing that term, what is called as, suppose Ns greater than Np, Ns greater than Np, it will be Vs greater than Vp. See this ratio, Ns greater than Np, Vs greater than Vp, and from this you can write it as Is less than Ip. And this is what is called as step up transformer, because we are increasing the voltage, the secondary voltage in which we are using the load that consumes the energy. So always remember, of course, those small details I didn't went into because this is a crash program. Detailed discussion is already done in the classrooms. Therefore, Vs greater than Vp, this is step up transformer. Step up transformer. Now exactly the opposite case. What is that? Ns less than Np, and as a consequence you will find Vs less than Vp and Is greater than Ip. This is what is called as, now you can see, since Vs is lesser, that is higher voltages are now reduced to smaller values, therefore it is step down transformer. Now step up or step down is only with respect to, yes, voltage but not current, do remember. Whether it is step up voltage or step down voltage, conservation of energy violation, the power in the secondary is same as power in the primary, ideally speaking. Why we are calling it ideal and what difference it makes in the practical cases, we should also see in the next small discussion. Having said this, one more important thing remember, that is, now Vs greater than Vp, Is less than Ip. Is less than Ip, the condition will be there if we provide the required possibility for Is to be less than Ip or for Is to be greater than Is, whatever it is, we have to provide the required conditions. Like what? Now, if I say Is less than Ip, definitely it should be the more resistance in the secondary coil and less resistance in the primary coil. So in the design and in the manufacture of that transformer, all these things to be taken care of, providing those conditions. It is just that does not happen for whatever design that we make. Is less than Ip, lesser resistance, more resistance in the secondary and lesser resistance in primary. Now, it can also be a conceptual question in the step down transformer, which of the following is true or false. If we say, see, high resistance means the coil with which the wire with which the coil is made of should be either thinner or thicker. It makes a difference. For higher resistance, once again our principle of current electricity are proportional to 1 by A. So for higher resistance in secondary, in the case of step down, it requires a coil made of thin wire in secondary and thick wire in the case of primary. Similarly, you can use the same for step down transformer also. Step down transformer also. Now, having said this, now when it comes to the functioning of transformer, let us define one more important parameter on which examples are based on. Any device, to know or to rate the functioning of the device, we define what is the efficiency, any device. Now in the case of transformer, we are now defining the efficiency as a ratio. Remember, efficiency for any device is a ratio of the same quantity. Here we have taken the ratio of powers in the primary and powers in the secondary. Remember, in the secondary coil of the transformer, we are now using the load that consumes the energy provided by the primary. Therefore, now the same symbols, P for primary, S for secondary. Okay, in the case of transformer, notations, P for primary, S for secondary, and supposing if I am using that capital L, that will be for the load which is connected in the secondary. Now, how do we define the efficiency? Suppose here in this example, the power in the primary, I am writing it as P for primary, and this is P. Yes, of course you have that load in the secondary, I am telling you, which I will take it as RL, and the power dissipation or power consumed at this load will be PL. Then we are defining it as, yes, output power upon input power we are taking. Output power. This is what is power in the secondary, power in the primary. And now, if see, PL is, if PL is power of the load, then PS will write as PI minus PL by PI. Is that okay? PI minus PL by PI will also be efficiency, where this PL referring to the power consumed at the site of the load. Therefore, the same way we can also write it as eta is equal to, earlier we said VSIS, because it is power in the secondary, and the denominator term is power in the primary, VP times IP. Now here, the term of ideal transformer, earlier we said PS is equal to PI, such that it happens only when there is no loss of energy. But in the practical cases, it is seen that this power in the secondary always less than power in the primary. Power in the primary, that is VS, IS is always less than VP, IP. The reason being, there are some sources of loss of energy which we will now discuss, important concepts only. And hence, eta always less than 1. That means efficiency less than 100%. We cannot have that. That is what earlier we said, ideal transformer, which does not exist. For that only, efficiency is 100%. And most of the time, see, this is how important it becomes when about reading a question. Most of the cases for our NEET and CET, of course, will be in case of ideal transformers. I can say 90-95% or even 98%. But very rarely some example may be there which is non-ideal or a practical transformer. And that is how the numbers should give you. As we have earlier mentioned that VS by VP is equal to the ratio. IS by IP is equal to ratio. If that, supposing IS by IP is not equal to NP by NS, what does it mean? Yes, definitely it means that it is a non-ideal transformer. Maybe a rare case, but the take from the data is very important. In some cases at least, eta less than 100%. As we have told you, what is the reason for this eta less than 100%? There are some sources of loss of energy. And what are those loss of energy is an important thing. So for that, the one is copper losses. Copper losses, which is nothing but because now here we are taking copper wire, laminated copper wire, wound on a frame, and in such case there is Jones heating effect through the coil which can be unavoidable. So unavoidable, therefore copper losses is one of the reasons for the efficiency to be less than 100%. And of course we can have minimization of these whatever sources that we are now mentioning. Copper losses due to Jones heating effect, and the second one is the earlier class we have discussed about is that hysteresis loss. Hysteresis, why it arises here in the case of transformer? Because here is a constant magnetization and demagnetization. Because AC, what happens? Increasing and decreasing and again increasing in the reverse ratio. Therefore, in the case of this core material, that magnetization and demagnetization will be happening, and in that cycle that hysteresis loss will be there. So hysteresis loss to be minimized, cannot be avoided, and how to minimize that? For that it is the choice of the material, and the choice is soft iron. Soft iron, for which of course demagnetization coercivity will be lesser and hysteresis is also less for soft iron. So this is, and one more thing is that one more loss is what is called as due to eddy currents. Due to eddy currents also, again see, eddy currents is very much similar to what earlier we have seen as self-induction. Self-induction is the case which arises in the case of a coil, whereas in the case of a bulk material, so whatever those induced EMFs due to change of flux, those currents what are called as eddy currents, again causing loss of energy. And to minimize these eddy currents, then the core material will take it in the form of pile of plates, not as a block. The frame will be taken as pile of plates. So this is also one source of. And number four, flux leakage is also a possibility. As earlier we have mentioned, whatever flux is provided by or generated or produced by the primary should 100% be linked with the secondary, but still for some reasons that flux linkage may not be 100%. So that is again a cause of loss of energy. And of course some trivial things also we can mention here, such as humming. During this entire mutual induction EMF in the secondary, and those vibrations that are set in the secondary will cause some loss of energy in the form of heat also. So this is about the transformer. We'll do a few examples again afterwards. So transformer ratio, step-up transformer, step-down transformer, conditions, the concept of efficiency. With these things, we'll now begin with some of the examples. Let us do some examples. All examples are very simple, but provided all those tidbits I have told you. Very simple things, large in number, the correction may be. So do practice, and now start with numericals. To begin with a simple example like AC voltage represented by. AC voltage represented by. This is the equation. Again, now the questioning is wide open. Like asking for RMS values, asking for average values, asking for frequencies, or asking for current equations, so on and so forth. Now, I will do some simple examples. Find RMS value. Find, instead of asking for frequency, find number of times current becomes 0. Find number of times current reverses in direction or EMF reverses in direction, likewise. Now in such case, our expression is E is equal to E naught cos of omega t plus phi is the general equation. I have told you it can be either sine function or cos function. The comparison of these things will give you the peak values. Peak value by root 2 is what is RMS value. Remember, average value 2 by pi times peak value will give you average values like that. So comparison will give you E naught is equal to 220 volts. Remember, this is the peak value, and the peak value is never shown by AC ammeters. So AC ammeter does not show 220, rather it will show the RMS value which is less than this peak value. And already we have mentioned that RMS value is 71% of the peak value. Like questioning and the wording of the question can make it from simple to difficult or complex, right? E naught is 220 volts, this omega here it is given as 60 pi. That pi term is also not always necessarily be given, do remember. Here I have shown, supposing if it is only 60 t, yes it can also be given. Don't make it a compulsion that it should always be in terms of pi, no, 60 pi t. Therefore omega value, which is 2 pi f, is 60 pi, and therefore this f is 30 Hz. F value is 30 Hz. Now when we know the frequency, what is the meaning of this frequency, earlier we have mentioned. One more time let us repeat. Frequency 30 Hz means 30 positive cycles in 1 second and 30 negative half cycles in the same 1 second. Remember, here it is and not or. 30 positive half cycles and 30 negative half cycles. What does it mean? You remember what do we mean by one cycle? One cycle, was our representation. You know that this is 0 to maximum, maximum to 0, again 0 to maximum. It is becoming maximum twice, right? Becoming 0 twice in one cycle. During one cycle this is the case. And therefore, now whenever we are given the frequency of, instead of frequency of the signal, if it is how many times current will be 0, the answer is 2f. So what is this 2f? 2f is the number of times for which current becomes 0 in 1 second, or current becomes maximum during 1 second, or current or EMF reversing in direction in 1 second. For all of them, the answer would be 2f. Of course, here this phi is what is that phase return, which is pi by 3. Now the point is that in the data, understand otherwise, it is given with an additional information such as a voltage signal in which circuit, whether it is R circuit or L circuit, a circuit with L or circuit with LR, circuit with C, circuit with CL, all those things are important. Without the mention of any such things, now we cannot predict whether it is, we cannot write, in fact we cannot even write the equation for current. Current signal equation can be given only when that information of nature of the circuit is given, resistor networks, inductor networks. Otherwise now here we cannot write it because no such additional data. So this is one such simplest of the cases. Now let us take one more case. What is that? Here you will find AC current is given by, and here you will find that I is equal to I1 sin omega t plus I2 cos omega t. Such expression is given. Now the question is, find the RMS value of the current, or the same we can also be asked for the nature of the circuit can also be given a comment, but with a lot of caution it should be made. Now first let us see. In such case, of course, let us do it in one or two ways. This I will write it as I is equal to I1 sin of omega t plus I2 sin of, yes, pi by 2 minus omega t. Cos theta is written in terms of sin of 90 minus theta. So what is that we observe? It is nothing but overlapping of two AC. It is overlapping of superposition of two AC signals. And do remember, whenever there are AC currents, AC signals, we have to follow the vector addition, the phasor diagrams. Therefore, when we see such case here, the phase difference between the two signals will be pi by 2. Therefore, what is the net current? We are talking about this I, this magnitude is equal to root of I1 squared plus I2 squared. Root of I1 squared plus I2 squared 2i1 into cos phi term, because of this pi by 2 it becomes 0. Therefore I is equal to, now we require that I RMS is equal to this I upon root 2. And here once again, we should be very careful, game all is not game. After doing all that final bubbling of the answer, till that moment we should have our conclusion. Because here there is a very easy possibility for making a mistake. Of course, though we know the answer, that blindfold sometimes bubbling will be wrong. To avoid that, I am telling you, please be very cautious. So root of I1 square plus I2 square dilute. Therefore, shall I write this answer as root of I1 square plus I2 square by 2, because it is also under root, whole under root. So this is where it becomes very, very important. Sometimes it is said as, suppose, root I1 square plus I2 square by 2. Or sometimes the options will be like I1 square plus I2 square by root 2. All such options will be there. So identifying that right option is very, very important. Therefore now here the answer is whole under root I1 square plus I2 square by 2 will be our RMS value. Similar example but with a small difference, right? Here I said an AC circuit with E is equal to, voltage equation given to be E is equal to E naught sin omega t, and the current equation is also given as I is equal to some equation is given. Now again the question is, what is the RMS value of current? It can be. RMS, which circuit, what is the nature of the circuit can also be a question, right? Let us see what will be the smartness or intelligence that we have to make use in that finding the nature as well. The same type of, here also you will find that a kind of superposition of two AC signals you will find. Again, in the case of sin theta and cos theta you will find. So as a result, yes, this I is equal to root of I1 squared plus I2 squared. Doing that, maybe one kind of answer. Right, that will give you rise to as, yes, it is 3 and 4. Therefore the answer is 5 ampere. This 5 ampere, how to say whether it is peak value or instantaneous? And that is why let us do it in other way. Like, see, a small simplification is like this. Suppose this is 3 by 5 sin omega t plus 4 by 5 cos omega t. I am just dividing and multiplying with this term 5. Then this is 5. This is of the function sin theta cos theta plus cos theta sin theta, which is nothing but sin of a plus b. Therefore this is sin of omega t plus 5 we are writing. So this 3 by 5, cos inverse 3 by 5, and this is cos inverse 4 by 5, which is written as now here 5. Therefore now this equation is in the general form, I is equal to I naught sin of omega t plus 5. Now the most important thing is finding the value of 5. Now therefore I naught is 5 ampere, the peak value, therefore the I RMS is 5 by root 2 ampere. Though we are doing all the cases of RMS value, it can also be asked for the average values. And here it comes the question of finding that phase difference and also the nature of the circuit. Here we will find this is 3 by 5. This is cos inverse 3 by 5. This is sin inverse 4 by 5. Any of them if you take, cos theta is equal to 3 by 5. Theta is nearly 53 degrees. We have used this ratio many times, and that is why I am making use it directly. Otherwise it will be given in the data. Don't worry about it. Supposing any such question asked for, this data will be there. Theta is equal to 53 degrees. Therefore now I am writing it as I is equal to 5 sin of omega t plus 53 degrees. Of course you can also convert it to radians, that by the 180 factor. You can also find that in If now this 53 degrees, now this 53 degrees happens to be the phase difference such that it is omega t plus. Now what is that voltage equation? It is going to be E naught sine of omega t. Now this is also sine and this is also sine. That is important to be seen. Otherwise, if it is given in terms of cos, we have to convert again this signal into cos wave, right? Cos of 90 minus theta. So both should be in the same function. That is one important case, sine of omega t. Now comparison of this phase term. Here this is only omega t, but this is omega t plus 5 by 3. Therefore here current leads voltage. Current leads voltage. It is a case of leading. I leads E by 53 degrees. So where comes the question of current leading voltage? Current leading voltage is a characteristic of capacitive reactance. Number one. When it is capacitive reactance, also remember that only pure capacitor, then that phase difference is pi by 2. This also we have mentioned earlier. If it is pure capacitor, pi by 2 current leading. If it is pure inductor, again phase is pi by 2 but voltage leading or current lagging. If it is other than pi by 2, then I have told you we should take care of either it is LR circuit or CR circuit or the LCR circuit. Therefore, here I leads by E by 53 degrees. It cannot be first thing pure R, no, pure L, no, pure C, no, and LR is also no, because in LR current will be lagging. So this is how we eliminate and find the answer. It cannot be LR also. Therefore, what is the reason? What will be our option? It is two possibilities again. It can be CR circuit or yes, LCR circuit is also possible. Where XC greater than XL case is arises. Therefore, the two possibilities are CR circuit and also LCR circuit. So this is what is how the concept is important. And that is why even before doing our examples, we are giving all those tidbits with as much as possible explanation. And that is why before you sit with your numericals, please go through the session once or twice, practice it. Whole lot of time is there with us in the world for our practices. This time a DC current I1 amperes superimposed with AC current I given by I2 sine omega t. It is a case of superimposition of AC and DC in a circuit. Find the resulting current or the effective current. Now, since it is the case of AC and we are talking about the effective, the question comes whether it is average value or RMS value. Since time has come, let us repeat that concept that for any AC signal, the average value over complete cycle is always 0. Average value over a complete cycle is 0 and therefore we define average values with respect to half cycles. Whereas, if we have to consider the full cycle of AC cycle in giving the effective values, we always write RMS values. And therefore, our answer now here is that since it is superposition, we will write I effective is equal to, this is I1 plus I2 sine of omega t, or this is what is I. Now I am writing I effective something. Yeah. This I is equal to I1 plus I2 sine omega t. Now I effective will define it as the RMS value over the complete cycle, which is integral 0 to t, the complete cycle, I squared dt by integral dt 0 to t. So this is a simple evaluation of the integral. Now since this is 0 to t integral dt, the denominator term will of course capital T. Therefore it is 1 by t times integral I1 plus I2 sine of omega t. One more time, I am sorry here. This is I effective squared value everything, right? So I effective squared value I1 plus I2 sine omega t whole square, which will give you this I1 squared. Next it is I2 squared sine square omega t plus 2 I1 I2 sine omega theta, right? Again, of course, integral 0 to t. A simple evolution. Now here comes a simple knowledge of our trigonometry. The average value of sine value or cos value, that is a periodic function over a complete cycle, is always 0. Integral sine theta, theta equal to 0 to 2 pi. Sine theta d theta is 0, similar in the case of cos as well. So integral sine theta d theta, 0 to 2 pi, that is what is the complete cycle, and that is equal to integral 0 to 2 pi cos theta d theta. This value is always 0. Average value of sine or cos over one complete cycle, 0. And one more identity that we are using is integral sine squared theta d theta, again 0 to 2 pi. If we consider this value is same as integral cos squared theta d theta, and this is what is 1 by 2. So those two identities are used for our final answer in this expression. Now according to that, so this will be, yes, I1 square, will get it as plus this I2 squared sine omega t, will get it as I2 squared by 2, because it is integral of sine square theta term, and this entire last term will be 0, average value of sine theta over the complete cycle. So this is what is I effective will be now under root of I1 squared plus I2 squared by 2. So that will be the case of imposition of AC and DC that is given, and this value, of course, as we told, effective means always the virtual value, the RMS value taken over the complete cycle. Now let us take one more example, and here the beauty is about the concept. See, appears to be simple, and of course it is simple, but committing that mistake I will mention here. The example says that an ideal choke coil, nothing but inductor. A choke coil takes 10 amperes of current connected to source of 125 volts, 25 hertz. Now, a pure resistor takes a current of 12.5 ampere under same conditions. For the same source, instead of inductor, if it is resistor, it is taking 12.5 amperes of current. Now the question is, find the current drawn by the series combination of the given L and R values. Same case of using our Ohm's law twice. How? We know that this I is equal to V by XL. For the case of pure inductor, we write I is equal to V by XL. Therefore, XL is equal to V by IL, which will give you as 125 by 10, that is 12.5 ohm. Now for the case of pure inductor, R is equal to only R is equal to 125 by 12.5. This will give us to 10 ohms, is it not? Resistor. Now we have to give the case of the series combination of L and R. Now this is what is a misconception that we have. When it is the series combination of L and R, it is not the case of two resistors in series. No, because in AC circuits, the case of impedance that we have told, when there are both X value and R value, the effective is impedance, which is not R1 plus R2, it is not R plus X value. How we have defined? Therefore, now we are writing for LR series combination, I is equal to V by Z, such that this Z value is under root R square plus X square is the result. So it is R square plus X square. Of course, this is now, this time it is XL square. This Z we need to evaluate, and then we will write this as 125 by, Now again this is 12.5 squared and 10 squared. Finding the answer. We should not do all those lengthy calculations, but in all such cases, options will definitely provide you a simple solution. You need not do the calculation. Answers will definitely tell you, and you do this calculation, you will find the answer. So in this case, we are not writing it as this. Though it is series combination, it is not the case of r plus x or x1 plus x2. It is the case of z that is evaluated and then currents are calculated. So these are the few examples, and tomorrow's class also will do all these numericals in AC currents. Have a good day. Practice well.